Yeah, is my screen visible and am I audible? Okay. So good evening to all. Welcome to the last session of day 2. So in this particular session, I'll be only showing you some demonstrations basically. Whatever we have learned till today, basically how to implement or how to implement medical image classification problem, and also I've chosen one segmentation problem, right? How to implement it with the help of k-means clustering and how to implement medical image classification problem. So I will check also, the chat box regularly. If you're having any doubt, you can directly interact with me. No problem. So before I show you some demonstration, so let me first summarize. Let me first discuss the different types of tools that are going to be useful for analyzing the medical images. As we all know that the images are nothing but, if you are storing the image in the computer, then it is nothing but stored in the form of a matrix. So what it seems, we are going to deal with the matrix, right? So the operations which we are going to perform, it is nothing but the operations over the images. So that means it is nothing but the operations over the matrix. So we need to deal with the matrix, and it is not a matrix having size 2 cross 2 or 3 cross 3 where there are only 3 columns and 3 rows. We know that the number of rows and the number of columns depends on the resolution of the image. And most of the time, the resolution of the image is very high. So that means we have to deal with a big size matrix or a small size matrix. So to deal with matrices, we have a lot of tools, libraries available in Python. If you want, you can also solve the similar. If you want, you can also deal with the matrix with the help of other programming languages or other tools like MATLAB and R programming language. But in this session, I'll be focusing on handling matrices and basically the images, medical images, and solving the image classification and clustering task in Python, and along with some of its libraries. So the kind of libraries which are very, very useful for us is NumPy. Panda is not that useful for our case because you're directly going to deal with the image, right? So NumPy is much more useful for us because this is one such package or library available which can be easily integrated with Python programming. We're mainly designed for dealing with large and multi-dimensional arrays, right? It can be a 2-dimensional array, it can be a 3-dimensional array, and more that. We'll see where and how can we apply this NumPy, right? Like these are like libraries, and you know how to import the libraries, right? There are codes available, like that's very similar to Java. It's like import NumPy, and there's alias name NP, right? And so you can use this name instead of the NumPy, right? Everywhere to call the functions, so to call the class. So these are like different modules we have, which can be easily integrated with the Python programming like NumPy, which is very, very important for us to create a matrix, to deal with the matrix, to perform some operations over the matrix. And here is just an example of how to create an array, right? Having 2 different elements like 0 and 6 like that. So similarly, pandas I'm not focusing on here. Probably you might have seen what do you mean by pandas is another library which also helps in analyzing the data and basically used for data manipulation, right? And where you can easily read the data if it is present in the CSV file and all. And if you want, you can also, it has a lot of other functions for analyzing, cleaning, exploring, and manipulating data. So similarly, there are some visualization tools we have like Matplotlib and C1. So we'll see some of its applications, right? How Matplotlib is also important for us. Sometimes if you need some plottings, right? If you need some 2-dimensional plottings and 3-dimensional plottings between, let's say, X and Y, right? Or X and Y and Z like that. So you can just call the functions, whatever is available with these Matplot libraries and C1 libraries. This is another scikit-learn is one of the most important libraries which is used to design, build the machine learning models, right? Or even to evaluate the machine learning models. We'll see how this type of, or how this particular tool is helpful in designing the classifiers, the regression models. But in our case, yes, classification model is very, very important. I think in my last lecture, I've already talked about that the whole structure or the overall structure of a machine learning based CAD system, where we have seen there are multiple stages, right? So starting with pre-processing, followed by ROI segmentation, then the feature engineering, and then something called as a classification stage. So in the classification stage, of course, we have to use the scikit-learn library, or else if you want, you can also write the code from the scratch using the traditional Python programming language. In addition to the classification algorithm, I mean classification models, there are few other methods which are very important for us to solve an image classification problem. We will see one is like trend test split. I will talk about it, how to split a data set into training and testing, and there's something called as validation as well. And there are a few other functions which are very important for us, like how to compute the confusion matrix. Probably you all know what do you mean by confusion matrix, and because from this confusion matrix we usually evaluate the performance of a model by computing the true positive, true negative, false positive, and false negative values of each class. Right? It can be a two-class classification problem. It can be a multi-class classification problem. So here is just an example how to just import this trend test split function. And this basically tells us that in trend test split function, you have to provide the whole data set, and then you have to also provide the ratio in which you want to divide that data set into trend and test. We'll discuss later on. And another very important library which is important for classifying the medical images, or probably, I mean, for solving any medical images task, is OpenCV. It is, of course, it's an image processing and computer vision library where you have to read the image. If you want to operate anything over the images, then you have to use this package, right, known as OpenCV package, and the name here is CV2. You can see here, I've written import CV2 to import the libraries, or to import all the functions and all of that is present in this particular module. And then I've just called a function called imread. This is the function which will help us in reading the image if it is present in the current directory and the current folder. If it is not present in the current folder, then you have to provide the whole path here just to read the image and store it in a matrix. Right, and if you want, you can just resize it. You can, the CV2 is having lot of different methods, image processing algorithms, I mean, that has been coded using, or has been provided using different functions that you can perform over the images. So this is very important as we are going to deal with the image. So you have to also use this OpenCV package, which is very important for us. There are a few deep learning frameworks which we have not yet discussed. About the deep learning models like convolutional neural network and few other advanced deep learning models, right? But still, we have to know that what are the frameworks or tools available for deep learning, and which are the most popular one till date. There are two. One is TensorFlow, along with the Keras, which is the wrapper, along with the TensorFlow, and there is something called as a PyTorch. So TensorFlow is basically developed by Google, and this PyTorch is developed by Meta or Facebook. If you want, you can design the deep learning model either using TensorFlow or Keras, or using PyTorch. It's up to you which one you should choose, right? Which one you prefer. But if you go through the latest research articles, probably you will find most of them are solving the problems using PyTorch, but still TensorFlow is people are using extensively, right? It's up to you. The similar kind of problem you can also solve using MATLAB, but we don't work with MATLAB since long time. If you just go through the top papers, like top journal papers and conference papers, they are also providing the GitHub link, basically the code link, and those codes are usually written either using TensorFlow, Keras, or using PyTorch. Right, so it is better to write the program or to implement the deep learning models either using TensorFlow, Keras, or using PyTorch. Right, again, there are a lot of functions available for both TensorFlow as well as Meta. The name tensor itself says that yes, we have to deal with the tensors, right? Either one-dimensional tensor or two-dimensional tensor or three-dimensional tensor. One-dimensional tensor means it can be a vector. Two-dimensional, it's a matrix. So three-dimensional is like it can be a volume and other kind of things, right? So we'll see one by one later on. I think I have to take another session where I will mention about how to, basically how I will demonstrate how to design convolutional neural network from the scratch, and how to design or how to use convolutional neural network using different strategies like transfer learning and all, and the corresponding demonstrations also I will show you. So similarly, PyTorch is also there. The syntax is different, but you can perform the similar type of operations. So there are some other tools if you want, I mean, like additional tools if you want, you can also use them. You can also import them for like augmentation. Image augmentation has become a very essential part in deep learning based models. So because generally in this particular domain of research, we don't have much data and we have limited amount of data. So if you want to just overcome those type of problems to some extent, then you can just use image augmentation strategies where you can apply some affine transformations like scaling, translation, rotation, reflection kind of thing to increase the number of images in the train set, and so that the model can also learn, the model can be a robust model and model can be robust towards this kind of transformations, right? So there are tools like augmentation is a tool where you can easily apply the functions to just perform augmentations over the images, like horizontal flipping, random crop, normalization, and so many others. If you want, you can also use this. And there are also so many other, Mona is a very popular framework, right? I mean, it's a very popular framework for developing and deploying deep learning models for medical imaging. And if you want, you can also use this one, right? Where you can design, it is basically built on PyTorch, and you can, if you want, you can design so many deep learning models. And if you want, you can also deploy it. Like there are several models already available. Like UNet is a very popular image segmentation, I mean, deep learning based or convolutional neural network based image segmentation approach, right? Which can be easily deployed here and you can directly use the functions available. Okay, so before I show you the demonstrations of the techniques which we have discussed, let me first show you something, I mean, which is very, very important, like what is the implementation setups? What are the steps to be followed to implement? What are the steps to be followed to implement any particular problem, right? Related to medical imaging. Let's say, for example, my goal is to classify uh, the problem statement is my goal is to classify that there are a lot of X-ray images, chest X-ray images given to me, and my goal is to classify those X-ray images, chest X-ray images, either into three categories. One is normal or healthy, one is COVID-19, and one is viral pneumonia, right? And we know that there are some similarities of, I mean, the symptoms, if you look at the characteristics. So COVID-19 is also having some similarities with the viral pneumonia. So this is just a three-class classification problem, right? It's a three-class classification problem. And our goal here is to classify the images either into three categories. There are three classes, right? So let me just write it down. The steps to be followed to implement this problem statement. It is just a chest X-ray image. I hope my screen is visible. Classification. And there are three classes as I mentioned. One is normal, I mean healthy. Second one is COVID-19. And the third one is pneumonia. Right? So what is given to us? First of all, the data, right? What is given to us? So what is given to us is nothing but a set of images. A set of images of these three categories: normal, COVID-19, and pneumonia. And that is what is known as a data set. Fine. What should be the next step? Is my screen visible? Let me check. Yeah. So I can see the chart box. Yeah, it is written yes. Okay, fine. Thank you. I will check regularly, right? So what will be given to us? That is, of course, a set of images. And what is our goal? To design a model based on these images so that in future, I will pass an unseen image or unknown image to the model, and the model will predict whether it belongs to normal or COVID-19 or pneumonia. That is what is our goal here. It is a classification task, right? Very simple problem. So to design the model, right, using machine learning, you know that there are two vital stages. One is training and one is testing. So training is basically, when I say training, so this is the model build procedure. So that means during training, we want to build the model, and testing is something very different. So once the model is built, you will just test the model, right, by passing some unknown images. So training is very, very important, right? And as we are considering an image classification problem, so usually the classification problem is supervised in nature. So that means a set of images is given to us along with the labels. Images along with the corresponding labels. So what are the labels? These are the three labels. This is given to us. So as we have to perform training first to design the model, we have to first split the data set into train and test, right? Because you do not have any other set or do not have, let's say, any unknown images. So what we have is this many number of images. Let's say, for example, I am having 1,000 number of images, right? And among them, let's say 500 images belong to one category, 300 belongs to another category, and 200 belongs to the COVID-19 category. This is what is given to us. And you all know, how can I split the data set, which is having 1,000 number of images? How can I split this into train set and test set? Right? Very, very important. Sometimes we also used to have another set known as validation set. I'll talk about it later on. Right? What is the meaning of this validation set and how it helps in overcoming some problems, right? Like overfitting and all. We'll discuss about it later on. So can you just tell me, I hope you already know that how to split. It's a very simple, right? I mean, there are various ways to split a data set into train set and test set. Sometimes, fortunately, the dataset inventors, basically the developers of the datasets, used to provide the train set and test set separately. Then you need not to do anything. So what you have to do is simply you have to take the train set, then process it, and then after designing the model, you can simply pass the test sets images, and then you have to evaluate the model. That's why. If it is not given, so this is the scenario, right, which I'm discussing, where the splitting or the official split has not been provided to you. Then what you will do? You have to split by yourself, right? And there is no unknown images, let's say, which is available. So what we are trying to do, we are splitting the data set into two parts, and we are passing the labels only during the training. We're not passing the labels during the testing, right? So we want our model to predict the value, and then we are having the target value, and this target value will be useful for us to evaluate the effectiveness of the model. I hope it is clear. So now I would ask you to tell me that what is the simplest procedure to divide a data set into train and test? I want to split, right? I want to pass few images during the design of the model, that means during the training stage, and I'll keep few other images or the rest of the images to evaluate the model. Now let me check the chart box. Yeah, I can see. So most of you have chosen 80 and 20, right? So of course there's a question here that why 80 20, why not then 70 30, right? So we'll discuss about this later on, right? So this type of questions I'm expecting from your side. Fine. So 80 20, okay, it's your choice. So let me choose 80% for training and 20% for testing. So that means I can easily compute here that out of 1,000 samples, 800 samples will go to training and 200 images will go for testing. Now there's a question here. It's very, very important to check So whether you have, whether you are applying 80% over the full data set or the whole data set, or you have to take something else, right? So that means my question is, I can take 800 training images, 800 images from, randomly, of course, it is random, right? So it is a random split. Randomly, you have to choose 80% of the images from the whole data set as a training images. Is it the correct way to take? Randomly 800 images from the 1000 images. So will there be any problem? Yes. Let's try to answer quickly so that I can discuss many more things. So is it the right way to directly choose randomly 800 images out of 1000 images? Yeah, is there any other procedure? Is there any other better procedure we can have? Yes. Okay, I got one of the answers like no. Okay, then if it is no, then what kind of procedures we can follow? Yes, absolutely correct. Right. So 80 from each is one of the answers I have got. Right. So instead of taking randomly 800 samples, right, I have to apply actually 80% over each of the class. You will also get 800 images, but we are giving same importance to each of the class. So if we are not applying 80% over each class, what will happen that you may have a training set having 500 samples, or let's say 490 samples from class 1, 250 samples from class 2, and similarly the rest others, maybe something around is very less, right? I think 60, probably 60 is the third class. We don't want this. The data sheet is not balanced already. So we have a lot of samples, more number of samples for normal class, less number of samples for COVID-19, and there is an average number of samples for pneumonia. And if I'm taking 80% randomly, there can be a scenario where there are 490 samples from normal, 250 from pneumonia, and only 60 from COVID-19. And with this, you want to train your model. This is not the right way. So what is the best way to do this and how to overcome this? Better to apply 80% over each class. So that means around 400 from this class, then 160 from this class, then 240 from this class. And the rest images can directly go to. And if you add them together, you will get again 800 and 200. Right? And this is what is 80 and 20. This is what you have to follow. Right? And this is sometimes known as stratified random split. We are giving equal distributions to each of the class, which is very, very important. That also we need to keep in our mind while splitting the data set by ourselves by providing some percentage values like 80% and 20%. I hope it is clear, and this is very, very important, right? So to deal with the imbalance issue, we have different techniques. We are not discussing about that. We are simply discussing about how to divide the data set into, or how to split the data set into train set and test set. I hope it is clear. So what is the next step? So now let's say, the splitting is done. We have set of images in the training set. We have set of images in the testing set. This is a training set and this is a test set. Of course, our goal is to build a model, right? But if I'll give you the data in the form of a table, if I'll directly give you some samples along with their attributes, the labels, you can directly, right? Like X and Y. If I'll give you X and Y, right? Let's say Xi and Yi, where I varies from, let's say 1 to 800, and these are all training samples. Right? Let's say these are all training samples, where Xi is nothing but a vector, let's say, for example, having dimension D, and all values are real values. If this type of scenario is given to you, you can directly apply the machine learning classifiers. You can directly train the machine learning classifiers, and you can directly pass these vectors into the machine learning models. But we don't have features. We don't have attributes. What we have is only the images. So yesterday only we discussed that can we directly process the image through the machine learning classifiers? Yesterday only we discussed. Yes, we know it is possible. Let's say I'm dealing with an image. Let's say all the images of this data set are of same size. For simplicity, I'm taking of same size. If it is of different size, you know, you have to resize all the images to same size, right? Or same resolution. Fine. So then what you have to do is, let's say all the images are having size, for example, 256 cross 256. And what is the simplest way? If you are not focusing on feature extraction, then what you have to do? So what you can do is you can just unroll this particular matrix, right, into a vector having size 1, 2, and so on up to 256 into 256. This many number of values will be there in the feature vector. This is one feature vector and this will represent one image. So similarly, you are having 800 images and finally the feature matrix will be having size 800 into 256 into 256. This will be the second dimension. I'm choosing, I'm just considering the samples in the rows and the features in the columns, right? You might have seen the reverse one, that the columns sometimes represents the samples, the rows represents the features. But I'm actually considering the scenario where the samples are in the rows and the columns basically are nothing but the features. Fine. I hope it is clear. But as I mentioned already, that now this is in this form, xi and yi. And now to process, and then what you have to do, what we are doing here, we are just converting, right, the pixels which are arranged in a two-dimensional array to a one-dimensional vector. And now the vector is a very, very high dimensional vector. It's a very high dimensional vector. You know that if I multiply 256 into 256, so it will be a very high dimensional vector. And we know if you want to, then what we can do, we can simply pass these vectors to a machine learning model. And then we will train the model. And once the model is ready, after training, then what you can do is you can just pass the test images, follow the same procedure to extract the features, right? And then you need not to train the model again because the model is already trained. So you have to then just pass the trained model, right? Let's say during testing, what you will do is you will be having some images, you will follow the same procedure to convert the images into the vector. That is the feature extraction procedure. Here we are not doing any feature extraction, simply we are converting, right? And then you have to pass to this machine learning model. The model has already been trained. That means the parameters of this model have already been optimized, right? If you are considering neural network, then the parameters like weights and biases have already been optimized. And you can just pass this vector to it and you can predict the values from other end. And this is like yt I'm writing for the test set. And let's say this is xt. Let's say this is the first sample I'm sending and you'll get a first value over here, right? I mean, this is nothing but the output level. So this will give you either a 0 or 1 or 2 or 1, 2, 3. So you may not, if you are using neural network, so you will get actually 3 probability values here, and based on the maximum probability value, you have to decide, right, which one, I mean, what should be the final level. This is what is the, the whole structure or the number of steps to be followed to solve the problem. But there is a problem here, right? So we know that we can't directly take this pixel values as the features. So there are a lot of issues with that. Right? We will lose the information, the spatial relationship, first of all, which is very, very important for us. The spatial relationships, like if there is a tumor here, so this pixel is related to this pixel is not related to this pixel, right? So that means we have to also preserve the relationship. That is what is the known as spatial relationship. The spatial relationship has to be preserved. And if you are just converting to a vector, so this relationship is going to be lost. Along with this, the dimensionality of the feature vector is going to be very, very high. So we don't want this procedure, right? We don't want this procedure. So then what do we want? We want to have a feature vector which is nothing but a representative of this particular image. We don't want to have a very big dimensional feature vector. We want to have a feature vector having dimension. Let's say this 256 in 256 can be considered as a D, which is the dimension of the feature vector, right? And now I can just reduce it to D days. I mean, I'm not reducing, I'm saying that D days is nothing but the number of features which can also represent the same characteristics of the image. So then which one is better? So D dash is much less than D. What is this D dash? D dash is nothing but the number of such features which are representing the same image, right? And we have discussed the same thing in the previous class, that how to extract the features. The features can be intensity based features, the features can be shape based features, the features can be texture based features, right? And yesterday we discussed one, I think I briefly discussed one particular technique which is known as GLCM. I hope you remember, right? Gray label co-occurrence matrix to get the texture features. So then what we will do basically there? Now we will pass every image and we will generate a gray label co-occurrence matrix. I've shown you in my previous class, right? On my previous talk, that what do you mean by this GLCM and how it captures the informations of different pixels, right? And what you will ultimately get if the image is having size, let's say 256 cross 256, and the GLCM I already mentioned, right? That what will be the size of the GLCM matrix. So GLCM matrix will depend on the number of levels, intensity levels we are dealing with. Let's say the intensity level is from 0 to 255. 0 to 255. So here the number of levels will be 0 to 255. Here also the number of levels will be 0 to 255. So you have to check how many times 0, 0 is present. Let's say horizontally. I told you earlier that there are two important parameters in GLCM. One is D, one is theta. D is the distance. And the default values are like 1 and 0. So that means along which direction you want to find out whether the pixels are repeated along the horizontal direction or along the vertical direction or along the diagonal directions. So for simplicity, I'm choosing the theta value as 0. That means I'm trying to find out the repeating patterns, which will basically tell us about the texture of the image, the repeating patterns along the horizontal directions. Right? So that means how many times 0, 0 is repeated along the horizontal direction in the image. How many times 0, 1 is repeated? How many times 0, 255 is repeated? So similarly, you can compute the counts for all possible types of intensity values from 250, 0 to 255 to 0 to 255. I also mentioned in my last class that we cannot directly consider these values as a feature values. So we have to consider the numeric values, which can be computed from this matrix. And there are 14 numerical features Professor Haralik has proposed, and I have shown you that paper also, right? Where Professor Haralik proposed that there are 14 texture features, 14 types of features, which we can compute from the GLCM, right, matrix, and which can be considered as a texture features. So we cannot directly compute the texture features or the numerical texture features like entropy, energy. Here are some of the examples like contrast, homogeneity. So there are a lot of others. 14, right? 14 features you can extract. So every numerical feature defines important characteristics about the image, and obviously the texture as well. Entropy basically tells us the content, right? The average amount of content that is present in the image. So then how can we compute? We know the formula for the entropy, right? This is the formula. We have seen from your, even from the school mathematics, right? So that entropy is nothing but it is just minus summation pi log of pi, where this pi are nothing but the probability distribution values. But these values are not the probability values. So to first convert this GLCM into its corresponding NGLCM known as normalized GLCM matrix. And from that normalized GLCM matrix, which contains the probability values rather than the counts. So how it is possible? You have to just add all the values over here and divide every value with that value, and you will get a probability value over here. At every cell, you will get probability values, and you have to just then apply. And all these numerical features can be computed from this NGLCM matrix, not from this GLCM matrix directly. So you'll get some real-time values over here, real values over here, real values over here. Right? Let's say I'm considering 5 features. There are 14, but I'm not considering 14. Or let's say out of 14, I'm considering only 5 different types of features. Input image we have passed to GLCM. GLCM gives us GLCM matrix. From GLCM matrix, we have got n GLCM matrix, and then from the n GLCM matrix, we could able to compute 5 different features. And now I will store that features in an array, one-dimensional array. Feature 1, feature 2, feature 3, feature 4, feature 5. This is entropy, this is energy, homogeneity, contrast, and something else. So what you have to do is you have to pass all the training images, or you have to pass all the images, right, to this, but to a particular function, because we know how, functions are very good, right? So you can easily use the functions in this case. So then what do we have to do? We have data sets, we have split it into train and test set, let's say. And then what I have to pass is I have to simply pass the images into a function. Let's say I have defined a function. Let's say I have a function over here known as GLCM function, which will take the input and give us, what do you mean by this return statement within a function, right? So this function will give us, this function will ultimately return 5 features. And we have to define here, what do you mean by F1? What do you mean by F2? What do you mean by F3? It is nothing but just when we are applying entropy over the NGLCM matrix. Nothing else. It's very simple to understand, right? Because we are simply using the functions here. And what do you have to do? That for every training sample, you have to pass this function, right? Every image should be passed to this function, and that for every image you will get 5 features. Now you see, instead of having small d number of features, which is very high, equal to 256 into 256, now we are having only d days number of features. So in our case, d is 256 into 256, which is a very big number, and d days is now 5. Now you see there's a drastic reduction in the features. And if you can represent this, if you can represent the image using these 5 features, then why do we need this many number of features or this many number of pixels to directly process? Right? I hope you at least got my idea that why do we need the extraction of the features. And then we will talk about why do we need, these are handcrafted, why sir you are applying GLCM, why not to other algorithms, right? That is another question. That is our concern, that which algorithm should be adopted, but which feature extraction algorithm should be adopted here to give us better feature, right? And we are not focusing on that. We are just trying to see that whether we can directly process the images with the machine learning algorithms, or whether we should extract the features and reduce the dimension of the feature vector that can also be acted as a representation of the same image. So this is how actually we solve the problem, right? So once you will extract the features from all the images, you have to send it to the machine learning model. The model can be anything. Let's say, for example, I'm considering a neural network model, and you know how to design a neural network model, right? A traditional neural network model to solve this kind of problem, or to design or to train the model, right? So what you have to do, right? So the input, the neural network, I'm considering a neural network having, let's say, only one hidden layer. Let's say, for example, I'm not considering multiple hidden layers, right? If you want, you can include multiple number of hidden layers, right? For simplicity, I'm considering a single layer fit for one neural network, right? Even, Professor Tanvir has discussed about the randomized neural network like extreme learning machine, and I think random vector functional link network that can also be applied over here. Right? You can, if you want, you can also apply those things over here. So now who can tell me, let's say, how many neurons should be there in the input layer if I'm having 5 number of features? Now, if you look at the data set, if you look at the matrix, the data matrix has become, let's say, 800 into 5. Right? Why 800? Because we have 800 samples in the training set, and there are 5 features for every sample. And now it has become a matrix. It has become a matrix known as feature matrix or data matrix. And we have labels as well. So these are all Xi's. And we have also labels, corresponding labels, because we are going to deal with a supervised learning technique neural network. Right? We have X, we have Y. Now we have to find out the function. Right? That is the relationship between X and Y. And that is what is the model building process, the learning process. right? So now who can tell me how many number of neurons should be there, right? Because it is fixed. How many number of neurons should be there in the input layer? If you are working with neural network, I hope you can easily tell the answers. Yes. How many neurons will be there in the input layer? If you are dealing with a 5-dimensional data, it is dependent on the data actually. Yeah, I could see the answers. Okay, absolutely correct. And how many neurons will be there in the output layer? Because I'm going to solve a 3-class classification problem. So how many neurons should be there in the classification layer? Yeah, absolutely correct. Yeah, thank you all. Thank you all. So I could see the results. I could see the answers, right? It is 3. Absolutely correct. So let me then draw the diagram of the neural network. This is what is the diagram, right? And this is one particular, let me write down 1, 2, 3, 4, 5. These are 5 features and these are all connected, right? These are all connected, right? These are all connected, right? This means this is fully connected. So you'll get 3 neurons at the output layer. This is the only one hidden layer I'm choosing here. This is the input I'm choosing and this is the output which you are getting here. Okay. So we have a lot of samples here and there are multiple ways to train the neural network model. I mean, the training procedure can be, can be like batch wise sequential learning process, can be batch wise, can be like you might have heard about something called as mini batch, right? Can be a stochastic learning process, can be full batch, can be mini batch, can be a sequential, can be mini batch, or can be batch wise learning. So there are 3 different learning strategies which you can adapt it here. So I mean, sequential means you have to pass one sample, you'll get the error at the end, and you will then update the weights. I mean, using back propagation algorithm, that's what right? So batch is like you will pass all the samples, you will collect the errors for every sample, and they will take the average of it, and then you will pass it, right? Then you will update. Basically, after getting the errors from all the samples, you will update the weights. And mini batch is the most popular one nowadays, right? So it is just in between the sequential one and the batch one. So these are all learning process. Very, very important, right? Everyone is, I mean, everything is very, very important here. So now my question here is, yes, you all know that how to choose the number of neurons in the input layer, the number of neurons in the output layer, but always there is a concern how to choose the number of neurons in the hidden layer, right? Because there is no such rule available till date, right? There are a few theorems people have proposed, but there is no such hard and fast rule that whether you should take 10 number of neurons or 15 number of neurons, right? There's you can say it's an empirical one, right? Empirical you can choose, or based on your experience you can decide. And what you know that if you add more number of neurons, the model is going to be complex. Even similarly, if you add more number of layers, the model is going to be complex, and there is a possibility that the model may suffer from overfitting issues. That all depends upon the number of data which you are dealing with. That is fine. Again, another important aspect, right? Because this neural network is somewhat related to the deep neural network, and which will be discussed by many speakers, right, in this particular FDP. So let us also talk about the little bit about the loss function. The loss function, sometimes known as error function or cost function. I hope all of you know what do you mean by loss function, right? So initially these weights and the biases, there are also biases, right? All these weights and biases are taken randomly. I mean, all this W is a matrix here, right? Then there are 2 matrices here. One is input to hidden and hidden to output, right? So maybe WH and W are the 2 different metrics, and there are also biases. If you want, you can also include biases within this matrix, And if you want, you can also have bias vectors. For every neurons in the hidden layer, we have bias values, right? And we all know the importance of this bias, right? From the school mathematics, and the equation is mx plus c, right? We all know the importance of this y-intercept, right? So why do we need actually this kind of function, right? And what is the need of this bias? Basically tells us the position. I mean, basically tells us the position of the hyperplane, right? And this w basically tells us like the orientation of the hyperplane. If you just check it geometrically, that is fine. So my question is something different. Why do we need a loss function? Because of course we need a loss function. We don't know. We are randomly assigning the values here. And our goal is to backpropagate the errors. That means to readjust the error. How can I readjust the error? How can I readjust the weights and bias? By looking at something, right? By looking at something, that is the error. And that is where actually we need an optimization here. So optimization is very, very important. So that means for every x, you are computing, for every xi, you are getting something called as yi cap, which is the predicted value from the model. And there is also a y given to us. And this y is not, sorry, this is only y. And this y is the target value which is given to us. And it is purely supervised, right? And this is what is the predicted value. So we should check how this value is different from this. And that is why we need this. So, and it all depends upon this y cap we have got, not only because of the weights and bias of the last layer, but also the weights and bias of all the layers, right? So that means we want to find out, or we want to readjust the value of w and b in such a way that this y cap will be almost equal to y. And at that time, my loss or my error should be close to 0. And now the question is, as I'm going to solve a classification problem, so what kind of loss function I should adopt here? The very popular loss function you might have seen, or the error function you might have seen, is nothing but known as mean square error. So can I adopt directly this mean square function, or is it a suitable loss function for solving a classification problem? Let me ask. You can write your answers in the chat box. Can I consider directly the mean square error as a loss function for solving a classification problem? Is it a suitable choice for solving a classification problem? Yeah, I could see answers from Dr. Devendra. No, sir. Any other answer? If you go through the literature, very old literature, right? If you go through the very old literature, you will find people have used mean square error, right? And right now, right, there is a function available, right? So which is, I mean, there is a loss available, I mean, which is known as, I mean, the concept was there earlier, but people have not adopted, right? Just before, I think, but maybe 2010 or like that, right? So if you go through the old literature, I mean, then you will definitely find that people have used, sorry, I'm sorry. So people have used this mean square error also to solve the problem. But nowadays we are not adopting this. We are adopting a more suitable one. What is that? That is cross entropy. You might have heard about. The cross entropy is the loss function. Why we're adopting actually the cross entropy here? Why not mean square error? Ultimately, what we are getting from the model, 3 probability values. Let's say 0.5, 0.35, and 0.15. This is what I'm getting from my model. And what I know that to process, I mean to train the model, I have to first convert the classes. Previously, I was having labels like 1, 2, and 3 for first class, second class, and 3 class for the third class. But to get the error here, or to apply this cross entropy, or to compute this cross entropy, so what I have to do is I have to first convert this every class. This 1 has to be converted into its 1 hot encoding 100, 2 has to be converted into 010, and 3 has to be converted into 001, like this. So this is how I have to represent, right, the every level in the form of a 1 hot encoding. And now this is the target value. Now 1 is not the target value, right? So 1 has been converted into 1, 0, 0. And this mean square error basically tells us that how much y cap or y cap is deviated from the original y. But unfortunately, we don't have a single value or not that kind of deviations we are looking at here. So what we are looking at here, this is a probability value. This is also, these are all probability values. So these are like two probability distributions for us. This is one probability distributions. If you add them together, you'll get 1. And this is another probability distributions. If you add them, then you'll definitely get 1. And this is for sure. We know that this belongs to class 1. That's why we have given the highest probability value to this class 1. So here every neuron is like representing one class. And that's why you said me that yes, we have to take 3 neurons, right? So we have 2 probability distributions, and now we want to find out the difference or the distance between the 2 probability distributions, right? So if you are having only 1 probability distribution, so you can go for entropy. If you are having 2 probability distributions, and if you want to find out the difference or the distance between them, there is a concept known as relative entropy. And this cross entropy is nothing but a variant of the relative entropy. And cross entropy basically gives us the information about how a probability distribution is different from another probability distributions. And this is why we are using, right, this kind of, this is why we are using cross entropy in place of mean square error while solving classification problem. And if you look at the formula is like this. Yi, where you can say I can write yj here, and I can also write here yj cap, right? For every class, you can just follow the same procedure. Sorry, log, there is log term here, and this is the predicted value, and this is the target value, and these two are different, right? These two are different. This is y cap, this is y, right? So previously in the entropy, you have seen both the distributions. It is pi, or yi. Here it is different. One is y, one is y cap. So both are different distributions. So to compute the difference or the distance between, right, the 2 probability distributions, we have something called as cross entropy. And you can see there are 2 probability distributions. That's why the name is so-called cross entropy, right? And it can be a binary cross entropy. It can be a categorical cross entropy based on the number of classes you are dealing with. I hope it is clear, right? So with this idea, let us now move to, the demonstration part, where I will show you, how can we implement the same thing given a set of images, how to apply, right? I have not chosen any, pre-processing step here, right? So I'm assuming that my images are not contaminated or degraded by any noise, any blurring effect, and all images are of good contrast. That means there is no, low contrast. There's no low contrast based image I have in my data set. That's what I'm assuming. But if you're feeling like this, so what you can do that you can just go for few of the popular techniques, right? For noise reductions as well as for contrast enhancement like Clahe. You might have heard about something called as histogram equalization, and there is something called as adaptive histogram equalization, and there is something called as contrastive limited adaptive histogram equalization, which is a very, very popular technique. Still people are using before passing the model for feature extraction. They used to process this. They used to pre-process the image using this concept, right? Even if your image is degraded by noise, so you need to be very, very careful by removing the noise. Sometimes we also lose some of the informations, high frequency components. The most important informations like edges and all, right? The boundaries and edges, you need to be very, very careful while applying, while removing the noise or while applying the denoising algorithms. So you may lose some of the important informations which are very crucial in classifying the images into certain categories or probably for some other problems, right? So this is, all about, in place of GLCM, you can just replace this GLCM with, let's say, some other algorithms, and you will get a set of features, representative features, and then you will pass it to the machine learning model. So the procedure will remain same, the steps will remain same, right? Only the algorithm will be different. For feature extraction, even for classification, instead of this neural network, you can either choose support vector machine, machine, you can choose decision tree, random forest, whatever you want to choose, right? There are multiple number of classifiers available, but always there is a concern that which one I should consider, right? So why I've actually discussed neural network today, because what we know that we are going to deal with convolutional neural network or probably some deep neural networks in future, right? And that's what I've focused mainly on this neural network, right? So hopefully you got the idea how to implement, and let us now move on to the, I will just show you, just show you the codes which I've already written and the outputs are already there. So I hope you'll get the idea, right? So later on, if you want, I can share the codes with you. So you can just go through the code and you can check whether it is working properly or not. So there are multiple platforms on which you can write the code. So I've just chosen the Google Colab platform, which is easy for me. You can also choose Kaggle as a platform. You can install Jupyter, and you can install Anaconda, whatever you want to install on your system, which is required to analyze to load the images into it. So if you want, you can also install all those packages on your system locally, and you can also run it using any browser, like very popular Jupyter kind of things. But I have just chosen for simplicity, I have chosen Google Colab as my platform, right, which is online and very easy to install. But only one thing you need to remember. So while implementing the algorithms on this Google Colab, so you have to first load the data on the drive so that you can easily mount it from the drive, right? So you can only access the data if you are loading it on the Google Drive, right? That's why I've chosen this. And for simplicity, as I told, that this is a GLCM based medical image classification, where I've chosen two different problem statement. One is like skin cancer classification, and the other one is the problem which I was discussing, right? I hope my screen is visible. Yeah. Is my screen visible? Okay, thank you. Yeah. So as we all know that initially we have to install all the packages, the required packages, and then followed by we have to load the libraries using the import statement, whatever the libraries we need. And the important libraries, we all know that one is like CV2 to load the image, to read the image, to apply some functions over it, to apply some operations over it. NumPy, very, very important to deal with the matrix. As you all know that we have to deal with the matrix, because feature is also a matrix, image is a matrix, feature is a vector. Then you can combine them and make it as a tensor or make it as a matrix. And matplotlib is also required. And okay, I don't require this thing right now, this clustering kind of thing right now. So I will also show you one applications on k-means clustering for medical image segmentation, right? And what are the also limitations of it, right? So again, I've chosen a data set, the publicly available data set for skin cancer classification, which contains 9 classes. And these are some of the codes. As our first task is to load the data set, which is already available with us. And then the next task is very simple. The next task is just to check how many classes we are having and how many images we are having. Then these are some sort of code for this, right? How to check whether that particular folder is existing or not. If it is not existing, then it will tell us that the folder is not available, right? Or else it will provide us the number of images that belong to all possible categories. You can see that dataset is highly imbalanced, right? So this kind of problems will be discussed later on, right? How to deal with this kind of problems. If the model, if the I can say if the data set is highly imbalanced, then how to deal with this kind of problems, right? We'll discuss all these things later on. But this demonstration is only to show you how to just apply this GLCM, or how to extract the GLCM based features and pass it to a classifier to solve a classification problem, right? Yes. Then next is nothing, just to show you something. Some of the sample images over here, right? From different categories. These are all skin dermoscopy images used to identify or detect the skin cancers, a lot of different properties. And this is what is the, you can say, the function for the GLCM. As I already mentioned, that I'm choosing only 5 numerical features from the GLCM matrix. You see, this is a function, already predefined functions available we are using, right? And this is the library from where we are getting this matrix, right? You can see over here. grayscale matrix, and basically it is a GLCM matrix, and the output is nothing but the GLCM matrix. And here also you have to define the distance as a parameter. I already mentioned. Angle is also another parameter. How many levels you are having? 256, it is from 0 to 255. And normalized, whether you want to normalize or not. Yes, normalize for true. Symmetric is like whether you want to take, I mean, the symmetric matrix or not, right? So that is a different thing. And similarly, and now you look at here. So what you have to do, you have got a matrix, that's a normalized GLCM matrix. And what do you have to do? You have to compute energy from that matrix. And the formulas are already available, right? So if you want, you can also directly implement the formula to get the values, or else you can directly use the formula. I mean, directly use the functions. Only you have to mention the GLCM matrix followed by the name of the numerical features already available, right? And these are nothing but like the features for us. So we have just put those values in a vector here. Basically, it's a list, right? So you know that. So just, I mean, it's kind of array for us is a 5-dimensional array. So this is a function, right? So every time what you have to do is we have to pass all the, I mean, we have to pass the image here. Basically, what we are doing the same thing. We're passing the images, all the images, and trying to get 5 different features for each of the image. And then we are storing it in an array. And X and Y is nothing but the corresponding label. The label is already given to us. Fine. Then there is a code for trend test split. No problem. You know, you have to, I'm just giving it 0.3 means test will be 30%, training will be 70%, nothing else. And then implementation of the multi-layer perceptron or the traditional neural network, which I've already shown you. You can directly use the functions which is available from scikit-learn. No need to go for this PyTorch to implement the traditional neural network. But here in this case, I have chosen the PyTorch as a function. I mean, PyTorch libraries to design the the traditional neural network, where you can see the input dimension will be definitely 5. The first hidden layer will be having 64 neurons, then 32 neurons, followed by the 3 neurons, right? And these are some of the, I mean, these are basically this code is to design the neural network, which I've already discussed. Similarly, you have to decide the kind of loss function which you are going to use. The learning rate is very, very important. You all know, because these are all gradient based optimization techniques which we are using to optimize the weights and bias. So instead of taking stochastic gradient descent, which is very, very popular, I'm choosing Adam as an optimizer. But if you want, you can also choose stochastic gradient and rest other variants of gradient descent, right? And I've chosen the number of epochs would be 4000, and similarly the cross entropy loss. And then what you will do, your task is to train the model, right? We are not training the feature extraction stage, right? Where there is no training in the feature extraction stage. We are only training the neural network model, right? That's what we can train. And then after the training is complete, you can see over here now the training is complete. I mean, I'm just applying the train model. I'm just trying to evaluate the train model over the, I mean, this model.eval will help us to evaluate the train model on the test set, right? So this, and then to compute the accuracy, I have to pass the y test value, which is the value we are already having, and then the predicted value which we are getting from our model, and then we have to pass these 2 values to get the accuracy. If you want, you can also get the values in the form of a confusion matrix. We are not getting good results in this case. You can see there are a lot of misclassifications. Now the 0 is misclassified to 5. Even the 1 is having a lot of similarities with the 5 class. Right, so that's why there are 51 number of samples which are correctly classified for class 1, right, and it is purely misclassified to class number 5, and this is not a good result, of course, we know that, right? So just I'm trying to show you that how to implement this, right? So maybe because the data is hugely imbalanced, and this class particularly, if you look at the 5th number of class is having more number of samples, so most of the time the model is biased towards this class, right? And then how to get this? Again, you have to load this sklearn package to get the confusion matrix. And if you want to also find out like the sensitivity, specificity, all the performance metrics which are used to evaluate a classification model, that also you can compute directly from the confusion matrix. There are also functions available. If you want, you can also do that. The same procedure I've followed and I've applied over another data set which is having less number of images. You can see over here I've chosen a data set, basically COVID-19 data set, right? This type of data was very popular during the pandemic time, right? Because everybody knows that pneumonia can be easily identified through chest X-ray images and chest CT scan images. So then people started working on this, right? Even we also did a couple of works, but no, not using machine learning, of course, using convolutional neural network. We have developed several models, right? Fine. So now in this case also you can see there are 10,192 samples that belong to normal category, and there are only 1,345 that belongs to viral pneumonia category, and there are 3,616 samples that belong to COVID-19 category, right? So that means it is again, I mean, the normal normal samples are more compared to them, right? I mean, compared to two other classes. I mean, there are a little bit of course, there is imbalance. The data is imbalanced, you can say, right? So the same procedure I have followed, same 5 number of features. The code is everything is same. You can just see the chest X-ray images from 3 different categories, right? You can easily identify, right? It's very, see, I mean, if you want to find out the difference, I mean, the difference between these two images, it is pretty clear, right? You will find white shadow or patchy kind of things over these lungs, right? Which is black in nature over here. You can see, which is clearly, the lungs are clearly visible in this case, right? I mean, in case where the patient is not affected by any infection like COVID-19 or pneumonia. And there are also several other indications that doctors used to see, like some consolidations, I mean, shadows, and you can see the some like cloudy white patches over the lungs, so that the lungs is not visible properly, right? And if you now look at this here also, you will find similar type of, I mean, your observations, right? In this pneumonia, that's why I told already that COVID-19 is also having similar like kind of characteristics or indications with viral pneumonia. Even the symptoms are almost same. So like ground glass opacities and all you can see over here, right? And the same algorithms, everything is same, the same number of features. So now it is working well on this data set compared to the previous one, right? Because it is, the number of classes are less, and there are less number of, I mean, there are less interclass similarity compared to the previous data set. Right, so we are getting 82% accuracy in this case, and now this is the confusion matrix on the test set. Again, you can see here that this class is, I mean, the normal class, which is having more number of samples, is correctly classified compared to the other classes, and other classes are also misclassified to the normal categories, right? So because, and this is having high number of samples and it is biased towards this class, we need to be very, very careful. How do we avoid this problem, and how do we solve this problem? We will discuss later on. Maybe some other speakers will also talk about this. I talk about how to deal with the challenges whatever we face usually in the field of medical imaging, right? So another application, another kind of feature extraction approach, I think I have discussed already yesterday, that wavelet, right, which is a very powerful image transform technique where you can convert the image into a frequency domain, and where you will get some low frequency and high frequency components. I mean, every image can be subdivided into high frequency and low frequency components at different resolutions as well as at different scales, right? So basically you will get the features at 3 different directions. One is horizontal direction, vertical direction, and horizontal direction, vertical direction, and diagonal direction, right? So I've shown you the picture after decomposing an image into, I mean, using 2-dimensional wavelet, discrete wavelet. So that wavelet can have different, you can choose any mother wavelet because you can use any different functions. So we've chosen HAR wavelet is a kind of wavelet which is very simple, right? And every, I mean, if you look at here, so only we have made changes in the feature extraction function. Rest other functions are same, exactly same. Only this function is different. It was previously GLCM and now it is a wavelet based feature extraction. So what we basically did here, so we have applied, I mean, basically we have passed every image and went for the decomposition using wavelet, I mean using HAR wavelet, and the decomposition is up to 1 level. If you want, you can also decompose to 2nd level, 3rd level, right? Where basically this LL component is further divided into 3 parts, basically 4 parts. So in the second level, you will get 7 number of sub images or sub bands. So in the first level, we are getting, for simplicity, I have taken only 1st level decomposition where I've got 4 different sub images or sub bands, LL, LH, HL, and HS. I mean, these are nothing but the outputs after applying high pass and low pass filters. If you apply 2 low pass filters along with a downsampling operation, you will get this actually. So I mean, those who are from the signal processing background, the better know what do you mean by low pass and high pass filters and how they basically preserve the sometimes low frequency components and cut the high frequency components. Sometimes it cuts the high frequency components and preserve the low frequency components, right? So that is why actually low pass filter and high pass filter. Low pass filters basically like the popular low pass filters are like Gaussian filter, average filters, right? And like the edge based filters, like the edge based filters are known as high pass filters, right? Where you want to preserve the high frequency components like of an image like edges and boundaries, fine. So ultimately what we have got, so previously we were getting only one matrix, that's a GLCM matrix, and from that we were getting the numerical features. So what we did basically, I mean, instead of taking those GLCM features, we have first decomposed the image using a two-dimensional wavelet, and we have got 4 different subbands, and from these subbands we are getting the features, numerical features. For every subband we are getting numerical features, and then just we are applying those features into. If you want, you can do multiple things over here. If you want, you can directly choose these high frequency values or high frequency. Let's say you can choose directly the coefficients of high frequency subband, right, from this HH, and those can be directly considered as a feature. You have to only unroll that matrix into a one-dimensional vector, right? That will become a feature vector. If you want, you can also apply the energy, entropy, and some kind of texture features over this matrix, and you will collect the features, and you will just form a final feature vector having dimension. Maybe let's say you are choosing 5, 5 from each of these 4 matrices, you will get a 40-dimensional image and 40-dimensional feature vector, right? And if I pass this again, the same number of features to the same classifier, that is multi-layer perceptron or feed-forward neural network, having 5 neurons in the input layer, 64 neurons in the first hidden layer, 32 neurons in the second hidden layer, 3 neurons in the output layer. What I'm getting is an improved result here, 88.67. And let me show you the confusion matrix. The previous confusion matrix was this one. And if you just compare this with this, so the more number of samples are correctly classified using the wavelet-based features compared to the GLCM-based features. See, so this kind of, I mean, if you want, you can also combine them together. Then you can have you can see the impact. You can just fuse the features and you can see, you can check that. But you need to be very, very careful while combining the features, whether the range of the features are matching or not. Or else it will be difficult. Like sometimes some of the features values may lie from 1 to 1,000. Some of the feature values may lie from 1 to, let's say, 10,000. So you need to be very, very careful. So at that time, you can just normalize the features using some feature normalization technique, right? So like zero mean unit, maybe variance or unit standard deviation kind of, or else min max normalization kind of thing, to just before passing it to a machine learning model. That also you can do. Right. So let me show you the last part. I'll only take 2 minutes to complete this session. Right. So the last part is, I mean, an unsupervised technique. I mean, how to apply an unsupervised clustering technique, which is very, very popular, K-means algorithm, right, for solving image segmentation problem. So the basic difference between image classification and image segmentation is, in case of classification, we are ultimately getting a probability value, or you can say a label, right? If image is given to us, our task is to provide a label to each of the image. But in case of segmentation, the input is an image, the output is also an image, right? So input is an image, output is also an image. Fine. So then in the output image, what we are expecting? So we are expecting to locate the tumors in case of, let's say, brain tumor segmentation or tumor segmentation. I want to locate the boundaries. I want to locate the tumors, right? So we'll see whether K-means clustering is useful for us or not. It's a unsupervised one. It doesn't require any ground truth. We'll talk about it later on. There's a specific, you can say, session we have where the speaker will discuss about what do you mean by medical image segmentation and what are the possible methods available till date, right, to solve medical image segmentation problems, and how to even adopt the convolutional neural network and the advanced architectures like Bayesian transformers, even beyond that, to solve medical image segmentation problem. This is the simplest one, as we all very much care about the K-means clustering approach, which is used to cluster the samples of different categories. The clusters of similar categories, similar categories. So then can we apply also the same rule here, or the same algorithm here, to cluster the pixels having similar type of values? You can either choose the color values, the RGB color values, or if you're choosing with, if you are dealing with grayscale images, you have to look at the gray values. I mean, basically the gray levels from 0 to 255. If it is matching with the pixel values, then you can just make them as a one cluster. But in K-means clustering, you know that you have to first decide the K value. That is what is even the limitations of the K-means value. We don't know that how many clusters you should form initially. So it all depends upon the data, right? And very simple again. It is unsupervised one. You need not to train the model, right? So you'll pass the image to the K-means clustering algorithm. You have to only provide the number of clusters, that means the K value, and based on the K value, it will decide K number of random centroids, centroids, and then how this k-means clustering, the working principle behind this k-means clustering. You have to choose k number of centroids, then you have to find out the distance from every sample, from every point. In our case, it is a pixel for every point to each of these centroids, and then you need to identify the most closest center, right? And accordingly, you will design the cluster, and then you will change, or you will change the basically the center, right? So that means you will update the centroid, and then you will repeat the same process till there is no change or there is no movement of the cluster centroid. And that's what you have to do. The functions are already available to do that. The k-means, the k-means clustering functions are already available. These are some of the images which I've chosen from a public data set which contains 3 types of brain tumor samples: meningioma, glioma, and pituitary. There are a few samples where you can easily see where is the tumor present, right? And your task is to actually locate this. It's very, very difficult through k-means clustering to precisely detect the tumor, right? Because the concept is something very different here. So this is what is the code which I have, which I've used. There is already, I have already mentioned that it is already available in sklearn, right? So I've directly loaded that particular function, k-means, and I'm just directly using that function and passing that how many clusters, right? It is asking me that how many clusters you want to have. So I have just passed 3 number of clusters right here. And if you want, you can also change it, and you can get the values. Let's say for this particular, or for this particular image, what you are getting is this output. But you know that it is not locating exactly the tumor, it is also locating the similar kind of thing, right? In the tumor category, this is, let's say that this green color is basically highlighting the tumor region. At the same time, the other regions are also having green color, right? So that means this is not accurate. It is just a segmentation. You see how a image has been divided into multiple regions based on the similar behavior or based on the similar characteristics, right? So here are some of the other results. Here are some of the other results. Okay, you can see over here. Here are some of the other results on different types of images. Fine. We will see how to improve this, right, using supervised technique or semi-supervised technique, and how to improve, how to precisely detect the tumor with the help of convolutional neural network based, basically with the help of convolutional neural network based image segmentation approach. You'll see, which is very, very interesting. And most of them are also supervised in nature. When it comes to supervised, that means you must have input image as well as the ground truth image. So that means the leveling of images for a classification problem is very easy, right? The doctor will only, or the clinicians will only check the image, will tell yes, it belongs to, let's say, pituitary, or it belongs to meningioma. But in case of segmentation, the doctor has to annotate pixel wise, right? So I'll discuss later on that how to solve this segmentation problem with the help of convolutional neural network, and what changes we have to make in the classification based CNN network to solve image segmentation problem. I hope you got the idea at least that how to. Here are some of the other examples, right? If I choose, other examples, then how it will show me. The results are not accurate, you can see, right? Because it is only without taking any information. Without taking any ground truth information or level information, it is giving me the output, right? And that's why it is not that much accurate, and that's why people are very much interested in designing supervised based, image segmentation approaches, right? Even there are some, if you go through the recent literature, you will find there are some unsupervised or semi-supervised based image segmentation models available through a convolutional neural network, right? Okay, so I'll stop here. If you are having any queries, so I'll be happy to answer. Yes, I can see some questions. Can you kindly explain the high frequency and low frequency components in an image? Okay, so when I say the high frequency components, it's those components where there is a drastic change in the intensity values, right? When there is a drastic change, you will definitely find some edges, right? Some boundaries, and those edges are only visible because of the drastic changes in the intensity values, right? So those are like high frequency components in the image. Fine. Any other questions? Can you please provide any links or site for downloading oral cancer images? Okay, for doing classification work. For my work, I'm working on. So okay. Okay, so okay, I'm working on the same doing pre-processing on available histopathological images, contrast staging, both enhancement, giving it to the pre-trained model using BGG19. Okay, I think okay, I think you can drop me an email. I think there is a website. I found one GitHub link where people have given a lot of information about a lot of publicly available data sets on different types of cancers. So probably oral cancer is one among them. One of my student also has done some work on oral cancer. I will talk to her and I will get back to you, right? You can drop me an email. So I may send you the link if it is available with us, right? So if it is publicly available, then you can directly download, right? I will definitely get back to you, right? Please drop an email to me. Any other question? Okay, so I could see for multi-class classification of skin cancer images you used using CNN transfer learning. Could you provide? Yes, yes, of course. We will see. We will definitely in my next hands-on session. I will take the same data set otherwise, and I'll show you the results, right? By using convolutional neural network and a pre-trained convolutional neural network via transfer learning concept. I will definitely, okay, I will definitely show you the results, and then we will conclude which one is better, right? So let's not conclude right now, right? Because we have not yet discussed CNN properly, and we have not yet also discussed transfer learning. We will conclude this just after that session. Is that okay? And empirically we will conclude, right? Empirically we will conclude. Fine. One more question. Is it possible to improve the segmentation by using k-means on the pixel features extracted by CNN? Okay. See, I mean, we generally don't follow this procedure, right? Because our goal is not to actually cluster the features here. Our goal is to cluster the pixels in an image, right? So that is why we don't follow this procedure, because our goal is to cluster every pixel. You pixel wise you have to cluster. We're not interested in clustering the features like we have seen in the applications of k-means, probably where we have studied k-means or where we have applied k-means before. In that case you are simply applying the k-means over some sort of feature vectors, right? So we are not doing that. So our goal is something very different. Our goal is to partition the image into different regions, right? And that means we are partitioning the pixel wise, we are partitioning the image pixel wise, right? So I will show you actually why we are not following this procedure. Yeah. Will there be any hands-on session on fundus image segmentation and classification? Yeah, we don't have actually. I think see if we can have hands-on sessions on other data set. So I mean, like let's say X-ray and all. So you can also just the input is different. The input is different. Only the input is different, and rest other things are same. If it is fundus, we have a lot of. I mean, we have 2-3 lectures. Even I'll be speaking on fundus images for detection of several diseases, right? Like glaucoma, diabetic retinopathy, and all. Fine, but here I think I will not get time to discuss about. I mean, I will not get time to demonstrate something. But if time will permit, definitely I will demonstrate. Right? I mean, if I'm choosing some other data set, you can just replace the other data set with the funded data set, and you can go for segmentation. You can go for classification. There is no problem, right? What if you can store the location of the pixels for each feature? Difficult. See, whenever you are applying CNN, and basically whenever you are applying as CNNs, there are CNNs like FCN, SegNet, UNet, which is which can be directly used to solve image segmentation problem, right? So no need to use k-means clustering. It can be directly used for segmentation problem. That I will show you in my next lecture. But so then if you are not using those kind of architectures, encoder decoder architectures, and if you are directly using the CNN which you have studied, right? So this will the CNN basically, I mean basically the pooling layers of the CNNs helps us in reducing the dimension of the feature or the dimension of the original feature map, right? So then from, I mean, how would you then cluster the pixels? Because the size is pretty small. After applying 2-3 pooling operations, then let's say the original image size is 256 cross 256. You have applied 4 times pooling operations. And now after that, you are getting output of the CNN is like, let's say 14 cross 14. Then what to cluster there? Our goal is to cluster the pixels, but we don't have that many number of pixels after applying several layers to convolutional neural network, right? So there is no meaning of clustering over there, right? But if you want, you can verify, let's say, if you can verify whether the features of a particular class it belongs to one, I mean, belongs to one cluster or not, the features of another class belongs to one cluster or not, that you can check, right? Just to check the discriminant ability of the model, right? That we usually do for classification task, but not for segmentation, right? Yeah. So any other question? Yes, shall I stop here? Yeah. Okay. Thank you so much. Okay. So thank you all. Good night, and we will meet again tomorrow at 4 p.m. Okay. So I request all the participants, please attend all the sessions because all the sessions are very, very useful and informative. And the